class. So Zina asked me to talk about modal logic. So we're going to do a judgmental reconstruction. Website, their PDF is corrupted, but the PDF I posted in the Slack channel should be fine. So we'll figure this out. The two teams of note takers have already taken their notes, so that's awesome as well. So there should be already some stuff out there. And I did also post two videos which sort of relate to what I talked about today. But in particular, if you want to look at some of the background material today, I'll post that also in the Slack channel. It is based on a journal paper by Frank Fenning and Rowan Davis, which is called the Judgmental Reconstruction of Modal Logic. And they also have a Journal of the Museum paper where they show how this modal reconstruction feeds into this idea of stage computation, which I'll mention later on as well. So, and then later, about 10 years after they've done that original work, we extended this work to something called contextual modal type theory. So hopefully I'll have a chance to talk about that as well today. So what's the slogan for today? Okay, the slogan for today is truth is living in the moment. I should write living in the moment. Here and right now. Validity is living forever and everywhere. So that's the slogan for today. So we'll in fact distinguish that.
What about possibility?
Oh,
the lowly
not
possibility.
possible today.
Everyone hates on possibility.
The world is full of possibilities, just not today. Some other day. It is possible that there is some other day where it is possible. Okay, so Valeria talked yesterday, we've already a bit about modal logic, in particular about the necessity modality. Which is often written as box A. Okay. And intuitively, it means that A is necessarily true. Okay, so really it means it's true everywhere. Okay, so it's true everywhere and forever. And so we'll interpret box A, in fact, as a validity, as a proposition A that must be valid. So we'll distinguish between truth and validity to sort of give a judgmental reconstruction, essentially of some of these modal systems that are out there. And modal logic is something that goes back, I don't know, 100 years. And it's really based on these ideas of accessibility between worlds. So something is true in a particular world, and then you have these accessibility relations between worlds. Okay? You can say, you might have transitivity, so it's true in my current world. Then you can go and step to your next world. Okay? Where by transitivity, you can sort of import it. You might have symmetry. Okay? So you might have different laws about these kind of accessibility relations. But the box modality has very specific laws. It has this law of reflexivity and transitivity of this world relation. And so people were interested in how we can describe these systems, not only model theoretically, but also sort of in a natural induction style. Right? And then around 2000, Frank and Rowan were really interested in understanding how these ideas from modal logic could be used to shed light on some computational concepts we have in the program. So I'll give you a very sort of their take on it, okay, which I think resolves a lot of issues that have been there. Right? So when I present some of these ideas, they might look like, oh, this looks beautiful. This is always how it has been. Okay, but that's not the case, right? So Providence in 1965, but you had a particular rule for this box modality, but that was actually not locally complete. Okay, I think Valeria touched on some issues, and some of the formulations didn't have substitutivity, for example. And so this formulation here is a particular nice formulation that resolves many of these existing issues that were there. And it gives us a very nice computational interpretation. Okay, so, and as we go along, I'll touch sort of on some of these design decisions that arise. It will also give us a chance to revisit some of these ideas of local soundness and local completeness. Okay? And I'll show you some applications of these ideas, so how we can actually write programs based on these ideas. So we'll see how far we get. Okay? All right, so what's validity? Okay, so we're going to say that if A is true unconditionally, so it's true under no assumptions, okay, then A is valid. And we can also say, okay, that if A is valid, then, well, A must be true. And in particular, it is true even in the presence of weakening. Okay, so it has some additional assumptions. So this is to accommodate for weakening. I don't know what it's going to accommodate anymore. Allow. So we'll introduce a judgment of two zones. Okay? So our main judgment will be delta, and will contain our global and valid assumptions. And we'll have gamma. Okay, so these are the assumptions that are true everywhere. Okay? They live forever. And our local assumptions are the ones for here and now. And under both of these, okay, we can then establish the truth of the given proposition. Yes?
Can you establish the validity as well?
So the validity comes into when we define the box, because we want to think of proving that box A is true and showing that A is valid. But we also know, okay, that if A is valid, what it means, essentially intuitively, as we will see, is that it cannot depend on my assumption here and now, but it can, of course, depend on other assumptions that live forever. Okay. So this is how it will come in, but will not introduce a separate judgment of A value. So, so these sets of assumptions, okay, are essentially of the form x1, a1 valid, xn, an valid. Here, and these assumptions are of the form a1 true, like the ones we've seen already. B1 true, yk, k true. Okay. So these are the assumptions we had before, okay. But now we have the power to have assumptions that tell us something more global about the state of the world. So, all right, so there are now two hypothesis rules, okay, in the system. The one we have always, which is essentially saying that, well, I can prove A is true if I have an assumption that says A is true in gamma. So, I mean, if I know here now that A is true, that I made this assumption A is true, then I should be able to prove that it is indeed true. Okay. So that's the one rule we have. But now we have a separate rule that essentially will say, that should be, if I know something, or if there's something that lives forever, okay, then I know that it is now true for me as well. Okay, so X denotes an assumption A valid in delta, then I should also be able to conclude that it's true for me. Because everybody believes it, okay? Okay, great. So the rules for conjunction are just the same, okay? We'll just keep the delta around. The rules for implications, we'll keep the delta around. Okay? Rules for disjunction, we keep the delta around. Nothing really exciting happens. What is exciting is maybe then the box rule. And so if we want to prove that box A is true, meaning that A is necessarily true, okay, and that means it must be valid, because it must be true forever, for everyone, everywhere, okay. It means that it cannot depend on my assumptions that I'm making right here and right now. So really I must drop these assumptions. And this is essentially how we're thinking of validity, because we're making no assumptions about them, no local assumptions about them, but we make local assumptions. Yeah.
Can you make local assumptions that are global? Can I locally assume, can gamma contain square A true?
Yeah, absolutely. Okay, good question. Because we want to actually prove something, okay, so for example, I might want to prove that box A implies A to be true. Okay. And this is definitely a law I want. Okay. It is indeed one of the laws of modal logic. Oh, dangerous thing. And but we're not quite rich in, not quite in a position to actually prove this, because all we can do for now is that we only have two zones, and all we can do is we can use our implication introduction rule and make an assumption, but that assumption will go in here. And I need to prove that A is true, but I haven't really shown you how to use an assumption box set, right? How to get information out of that assumption box set. So we're not quite ready yet, okay? So, but I want to point out one thing about this box connective that we're introducing. It is internalizing sort of this idea of validity. Okay, so I talked about hypothetical reasoning, right, when we were reasoning by assumptions. So we said, oh, we have an assumption, under this assumption we can establish some proposition E, and then we internalize this hypothetical reasoning using the implication sign. And if you would have a universal quantifier, you would prove that something is true for some parameter, say some abstract parameter name, A. You prove P of X, that P of A is true. Then you know, because you didn't make any assumptions about this A specifically, you prove this parametrically for A, you know this is true for all X, P of X. Okay, so we internalize parametric reasoning using the actual quantifier. And the box modality is in some sense internalizing reasoning about validity. Right? It gives us a way of stating and distinguishing between propositions that are valid in our actual statement, for example here, and propositions that are sort of true in my current world. So this is essentially, I should be able to prove that if it is true forever, okay, and for everyone, everywhere, then it is also true here, in Oregon, Eugene, law faculty. Okay. So there are different formulations of the box introduction rule. Okay, so indeed, I believe Valeria showed you one yesterday, and that formulation, for example, was something like this. And then prove that A is true under this box gamma. So this is a rule actually that goes back to Providence, 1965. And you see that it sort of has a resemblance, but it doesn't clearly distinguish between these zones of things that are valid, because this is morally what our valid context is. And this is morally what our true assumptions are. Okay, so this is more like local, and this is our global. But it doesn't separate them specifically into these two zones. Rather, it has sort of a side condition or a specific notation that sort of says, you know, okay, consider all these boxed assumptions and keep them in the premise, okay? And one of the issues that comes up then in this rule, and especially together with the elimination rule for this rule, is essentially that weren't able to compose derivations together. Okay, so you basically don't have a substitution lemma for these assumptions that are boxed. And so this formulation here resolves this in one particular way. Valeria had resolved it in her work in a different way. But this is sort of a solution to this where we basically separate this out in two different contexts, clearly. And it gives a very simple introduction rule for box. Yeah.
So for this box modality internalizes the validity for the top top right rule and hypothesis, why are we not directly able to conclude that we get box A true?
Here,
Yes.
because we only would get A is valid, and we would still need to introduce the box. What do you, sorry, maybe I didn't understand your question.
Right. So like, wouldn't it be stronger to just say that box A true because A is
Box A true here?
Yeah.
It's stronger, but it's sort of too strong because we want to basically import the fact that something is true everywhere in your local world. You want to have the fact, you want to have this law. Okay. And the only way we can prove this law is going to be if we actually say, can conclude, follow, right? So if something is valid, we can actually conclude that it is true. And it is one of our definition of validity, in fact. Okay? The second part of this definition of validity says that if A is valid, we can conclude that it is true. Okay? So if you would keep the box, well, it's actually too strong. It also is sort of not really introducing the meaning of box. Okay, so that's another way of thinking about it, right? I mean, I said on this judgmental view, I said I want to introduce the connector. Okay, I want to introduce the box A, and I kind of think about what does it mean. Okay, declaratively to me to be for box A to be true, and essentially it means well, A must be true without reference to any of my local assumptions. So I haven't given you yet the elimination principle, but I would like to basically contain, right, the definition of box in the introduction and elimination rules. So this isn't completely wrong to add a rule that says, from my assumption invalid, I can conclude box A, but it doesn't really allow you, it doesn't give you the full power. Yeah.
Maybe another way to rephrase the question is, could I add a different inference rule that was delta gamma proves box A, and then the conclusion is delta gamma proves A is true, and then I could change that rule to box A in the conclusion.
Okay, yeah.
But maybe.
Sorry. You can tell me. So what do you want to do?
So maybe the question was like, if you have a rule that says delta gamma proves box A in the hypothesis,
Yeah.
and then delta gamma proves A in the conclusion, then you could change the top right rule on the middle board to say box A in the conclusion.
Okay, so this is a possible elimination rule. Okay. So let's see if it's locally sounding complete. Okay. All right? Okay. So what did we say? We said local soundness was introduce and eliminate. Okay? So I'm going to introduce a box. Okay, so that's my box introduction. Yeah. And this is the purple elimination rule principle. Yeah. So we conclude A is true according to this rule over there. Okay, you're like thumbs up, yes. Okay. All right. So local soundness says I need to have had a proof of gamma A true. And how would I get that proof?
You got it technically,
I could beacon, okay, so it seems locally sound. I could take this derivation, right, and plug this in here and say apply beaconing. Okay, so it seems definitely a sound thing to do. All right, so let's see if it's locally complete. Okay. So what does local completeness say? So we have a proof of box A, and we need to be able to expand it. Okay, so we need to come to the path where we have here box A, using somehow this as an assumption here. So somehow this and we need to have some kind of add it in, back out, something, okay? All right, so what I can do is I can use my box introduction rule here, okay? But my box introduction rule will drop the gamma. Yeah? All right, so how do I go between these two?
You can't.
I can't, that's right. I mean, it's certainly not the purple rule, because the purple rule requires me to have like all this stuff in there. Okay. And so the problem is, right, I cannot use here this purple elimination rule to close the gap. Okay. So this is indeed, people have proposed rules like that, okay. But it's not a good rule. And to make you feel better, you're not the only one who has proposed it. And Providence has a not locally complete rule as well, so you're like in good company. But I'll raise it anyway. It's not what you want. But how do we resolve this issue? Okay, so we want to have a more general rule. And the answer to this is essentially that we want to think of this more as a let-style elimination. Try and squeeze in here. What do I mean by a let-style rule? So it's a bit like the disjunction rule. Okay, so you have here box A is true. Okay, for some reason you have this fact. And if you can then prove under the assumption that A is valid, so now we have this additional assumption. Okay, so we have this new assumption that we can add, so we make sure it is preserving forever, for eternity, it will stay there. Okay? And I have some assumptions, gamma, and I can prove C is true. Then I have a way that I prove C true without this knowledge of box A. So it's a bit like the disjunction rule. The disjunction rule had two branches. Then we said, if we were able to prove A or B, and we were able to prove C under an assumption A and C under the assumption B, we were able to prove C. So it introduced this case analysis, A or B, we prove C under A, we prove C under B. That meant we had a proof of C. Now here we don't have two branches, but we basically say, if we were able to prove that A was true necessarily, and we're able to prove that C is true under this assumption A valid, then we know that C must be true. Basically, we only rely on things that were true forever to begin with. So let's see if this locally sound and locally complete. Okay, so we'll introduce and eliminate. Okay, so A true. We introduce box A true. Okay, that's our box introduction. And then we eliminate. And since I was so pedantic with all my superscripts previously, okay, so there is a local scope or local assumption that is being introduced, that is the U. And so I unscript squeeze this U up in here. Okay. I know you guys can't see it, but this is the thing that gets bound. So here you'll see it better. Okay, so there's this assumption U that gets introduced. Okay. And under these conditions, we have that C is true. Okay, so now we need a proof of C is true. And how do we know we had a proof of C true? So our local samples argument is a little bit more complicated now than what we had before. But what is the idea? Okay? Well, previously, we had this idea that whenever we had assumptions true in here, we have the substitution principle that basically said if you have a derivation that depended on an assumption A true, and you had a proof for A true, then you didn't need this assumption. Okay? You had a proof of C without referring to the assumption, because whenever you needed to refer to A, you proved A. So now we have another substitution lemma, and that substitution lemma combines this part and this part, and it essentially says whenever you need this assumption that A is valid, you can use this proof, B, which already says that A is true under no assumption. So the substitution lemma we now have, the additional substitution lemma, okay, so we have in the each2, the old one, okay, which says if I have an assumption X A true, and I prove C is true, and I have an assumption that I have a proof that A is true, then I have a proof of C is true. Okay, so we are substituting for our assumption that which says A true, but we also have this one, okay, which essentially says that if you have a valid assumption, and you have a proof of C true that might depend on this assumption, and we have a proof of A true, or you cannot, which means essentially A valid, okay, according to our definition, then we have a proof that does not